Welcome to the Problemas channel, Season 2, Episode 36, the episode which I titled A Show of Equal Distances, because in this episode we will solve a mathematical problem in which we're given two pairs of equal distances, the equal distances from the point C to the points M and N, and the equal distances from the point O to the vertices of the parent triangle A and B, and under conditions specified, there is another pair of equal distances lurking somewhere over here, but this is exactly what we will discover in this episode. But before we do that, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, welcome to our channel and thank you for your vote of confidence. And second of all, it is a good idea for you to go to the home page of this channel and in the channel's trailer section, find the episode titled The Problema Channel's How To. Watch that episode in its entirety, follow all the instructions that were given in that episode, because in this episode we explain and motivate everything that we do on this channel. In the mathematical problem S2M38, we're given a Euclidean triangle A, B, and C, and on the side of that triangle CA, they're chosen a point M in such a way that the distance from the vertex C to the point M is exactly the same as the distance from the same vertex C to another point N that is chosen on the side of the parent triangle CB. This is reflected over here. The length of the line segment CM is exactly the same as the length of the line segment CN. Moreover, we're told that the vertex A of the parent triangle is connected with the point N on the side CB, and the point B, or the vertex B of the parent triangle, is connected with the point M that was chosen on the side CA of the parent triangle, and the line segments AN and BM intersect at the point O, as reflected over here. The line segment AN intersects with the line segment BM over the point O. And we're told that the point O has the following property. It is equally distant from the vertex A of the parent triangle and from the vertex B of the parent triangle. We reflect that condition over here. The length of the line segment OA is exactly the same as the length of the line segment OB. We're also told that the magnitude of 1, which 1 is not specified, the author of the problem left this specification out apparently, and we're told that the magnitude of only one interior angle of the parent triangle ABC is known ahead of time. Let us say it is given, and we designate it with the alpha 0, which means that in this case the magnitude of that angle can be the magnitude of the interior angle at the vertex A, or the magnitude of the interior angle at the vertex B, or the magnitude of the interior angle at the vertex C. We do not know. We have to analyze the situation as our solution unfolds. And the challenge in this problem is to recover the magnitudes of the remaining two interior angles of that triangle. And precisely due to the placement of this problem, in the sequence in which we are studying the eliminate and conquer problem solving approach, in a dedicated manner, it is evident that one way to solve this problem is to use precisely the eliminate and conquer problem solving approach. A solution of any mathematical problem never comes to us instantly and pops out of the blue, for example. Quite the opposite is true. With each and every mathematical problem, we play and doodle, we fight and struggle, we try and fail many times before we may come up with a solution. But let us be frank and honest, more often than not we actually fail, and that makes the success or in the process of solving this or that technical problem that much sweeter and that much greater. And this problem is no exception. If we try to attentively and thoughtfully render the constraints of the given problem with the modern computer-aided graphical package. For example, I use a lot the free software called, let me write it down over here so you guys can see. It's called GeoGebra. This is the free software that I use. I install it locally on my Ubuntu or Linux flavored laptop, and that's what I use. If we try to use this package or a similar one, we will see that done professionally, so to speak, the conditions of the given problem will look as follows. Which gives us plenty of reasons to think that the triangle ABC in question must be actually isosceles. In other words, after playing around with the given conditions with the in the certain software package, in addition to two pairs of equal distances CM and CN and OA and OB, we think that there is another pair of equal distances lurking in this problem. We think that the distance from the vertex C of the parent triangle to the vertex A must be the same as the distance of the vertex C to the vertex B of the parent triangle. And if we can prove that somehow, then we will also see that the distance of the point O to the points M and N must be the same, and the distances from the points M to A and from the points N to B also must be the same. This is actually a bonanza of equal distances. That is why I titled this episode A Show of Equal Distances. But all the hunches aside, we need to somehow generate a proof that under the conditions specified, the parent triangle ABC is isosceles on the sides CA and CB, meaning that the lengths of the sides CA and CB must be equal one another. This is our hunch. And how do we generate such a proof? We generate such a proof precisely using the eliminate and conquer problem solving approach. But if you were solving this problem this way, what would you construct the elimination process on? Put this video on pause, think about it, come back, compare your ideas to ours. And my idea here is to construct the elimination precisely on the lengths of the sides CA and CB of the parent triangle. And in order to do that, we will use the Exactly. In order to prove that the parent triangle ABC is isosceles on the sides CA and CB under the constraints specified in the problem statement, we will use the so-called trichotomy law for real numbers, according to which if A and B are any two real numbers, then exactly one of exactly three mutually exclusive relations will hold. The real number A is strictly larger than or greater than the real number B. The real numbers A and B are of equal magnitude. A is equal to B and B is equal to A. Or the real number A is strictly smaller or less than the real number B. And the mutually exclusive here means precisely that if, for example, the real number A, if it so happens that the real number A is strictly greater than the real number B, then that means that the real number A is not equal to the real number B and is not less than or smaller than the real number B. If it so happens that the real numbers A and B are of equal magnitude, that means that it is not the case that A is greater than B, and it is not the case that A is smaller or less than B. And lastly, if it so happens that the real number A is strictly smaller than the real number B, then it means that it is not the case that A is equal to B and A is greater than B. And thus there emerges our battle plan. which is we will let the length of the side CA of the parent triangle ABC play the role of the real number A, and we will let the length of the side CB of the parent triangle ABC play the role of the real number B. Then we already know that to such two real numbers, the law of trichotomy applies, which means that magnitude-wise, only one of precisely three mutually exclusive relations will hold. We will then assume temporarily that A is larger than B, and we will use the mechanism called a contradiction to show that that is not possible. Then we will assume temporarily again that A is strictly smaller than B, and again using the same or the similar mechanism called a contradiction, we'll show that that is not possible either. Then by analyzing the conditions given in the problem statement, we will realize that it is entirely possible that this Euclidean triangle can exist, and that will leave only one possibility according to the trichotomy law for real numbers. A is equal to B, which again translated back from the world of real numbers into the given problem statement would precisely mean that the parent triangle ABC is isosceles on the sides CA and CB, meaning that in this triangle the length of the side CA must be equal to the length of the side CB. Before we walk into the weeds of this proof, I want to make sure that we all understand the two big components or the two big pieces of the upcoming proof: the tactical or the how, and the strategic or the what. The tactical or the how piece will be exactly that. It will be a contradiction. But the strategic piece or the what will be precisely that, the elimination or eliminate and conquer. And in this case, a contradiction will provide the means or the reason for elimination. Now that we understand how we will proceed further, let us carry out our proof. As such, we construct our elimination rounds based on a contradiction, and setting up a contradiction, we first assume that the real number A is strictly larger or greater than the real number B, which in translated back into our specific problem means that the length of the line segment CA, or the length of the side CA of the parent triangle ABC, is strictly larger than the length CB, the length of the side CB of the parent triangle ABC. And now we will loiter a little bit around the point O, and we will try to squeeze as much actionable mathematics from the information given about the point O as possible. And what does that mean? Well, we're told that the point O is equidistant from the vertices A and B of the parent triangle ABC. And what does that mean? Well, that means that we may or may not have proved this on this channel, but it is not that difficult to prove, and you guys should try to generate a proof of your own. But that means that the point O belongs to the perpendicular bisector of the base or of the line segment AB, which is the side AB of the parent triangle ABC. I show it here in yellow, and this angle over here shown in yellow is also right. And the way these things work is that the underlying if P then Q implication is true both ways. In other words, if a point X belongs to the perpendicular bisector P, marked over here with the lowercase, then that means that the distance from that point X to the vertices B and A is one and the same. And conversely, if a point X in the parent plane is such that the distance from that point to the points A and B is one and the same, then that point necessarily belongs to the perpendicular bisector of that line segment, which is basically another way of saying that the perpendicular bisector P, shown over here, is the set of all points in the parent plane, each of which is equidistant from the points B and A. And moreover, if, for example, we were to step out of 2 space into 3 space, then the plane that cuts the line segment AB in half and perpendicular to it that runs this way, then that plane will be actually the set of all the points in the ambient 3 space, each of which is equidistant from the given fixed points A and B. Two planes intersect over a straight line, and in this case that straight line is precisely the perpendicular bisector lowercase p. Now, what does that mean in our case, in our assumption? Remember, setting up a contradiction, we assumed that the length of the side CA is strictly larger than the length of the side CB. Well, that means through all the analysis that we just carried out with respect to the point O, that means that the perpendicular bisector P of the line segment AB will intersect the side CA of the parent triangle at the point P, which is necessarily what? In between the points A and C. And that much should be straightforward to see. For example, recall that if we have, I'll draw it over here by hand, if we have 2 points, A and B, for example, like so, we cut this line segment with the perpendicular bisector in such a way that the length of this line segment is the same as the length of this line segment. This angle is right. We pick a point over here. Let's say this is our point C. What does that mean? It means that the distance CB is exactly the same as the distance CA. But in our case, under the standing assumption, we move this point away off the perpendicular bisector to, let's say, over here. This is where our point C lives right now, right here. That means that technically speaking, the point C is closer to the point B as it is closer to the point A. In other words, our triangle now looks as this way, and that way. You see, compare this drawing with this drawing, and this is effectively what you have. You have the point P sitting right here. This is our point P right here. So that means, let me erase. Now that we understand where did this observation come from, let me erase it, and admittedly abusing the mathematical notation that deals with the relations between the magnitudes of real numbers, we will steal the same notation, and we will say that in this case we have the following relation. The point A runs like this, P and C. This is basically, yes, I am violating and I'm abusing this notation, but we'll understand what that means. The point P is located strictly between the points A and between the point C, not outside this line segment on the closer to the point C, and not outside the segment closer to the point A, but it's strictly inside the line segment CA. This is what we capture with this notation over here. And once we understand what is going on, why this must be the case, then if you were solving this problem this way, what will be your next maneuver? What would be the next step that you make? Put this video on pause, think about it, and then come back and compare your ideas to ours. Thankfully, we're all wired differently and we all think differently. In real time, you may generate a different idea, and do not be shy. Feel free to share your idea in the comment section below. Here is my idea. I suggest that we connect the point B, the vertex B of the parent triangle ABC, with the point P, as shown over here in yellow. And because, remember, we spent quite a bit of effort trying to explain and convince ourselves that the point P sits strictly in between the points C and A. That means that the line segment BP will also fall where? In general, it will fall strictly inside the parent triangle ABC, as shown over here. And now, because again, the point N, in theory, we're not told, but in general, we take it that that point is also strictly in the general position between the points B and C. That means what? That means that the line segment AN lies strictly inside the parent triangle ABC. And that means that the line segments AN and BP will intersect over the point Q, shown over here in yellow. I captured that fact over here. The line segment BP intersects. This is the sign for intersection. We steal it from the theory of sets. With the line segment AN over the point Q. And it is important to understand that the point Q, again, the point Q, if we were to capture it, this point Q belongs strictly to the triangle ABC. Again, this notation a little bit poor. It doesn't really say that the point Q is strictly inside, but we understand that the geometry of this intersection means that the point Q is located strictly inside in the innards of the triangle ABC. And again, if you did not solve this problem correctly and on your own, as we explained in season 1, episode 2, try to not watch what we're about to present in its entirety. Try to think with us in real time. This is always fun. And as soon as you catch the whiff of what is going on, put the video on pause, walk away, and then try to solve this problem completely on your own. Try to carry your own proof all the way to the end, and then come back to compare your ideas to our ideas. So now that we had the bright idea to construct the line segment BP, intersect this line segment with the segment AN over the point Q, what would your next maneuver be? Well, more than 2,000 years ago, Euclid had something interesting to say about the following angles. Let's write it down. APB, we will call it the angle theta. Angle theta, it will be angle APB. I wrote it over here, so the angle APB will be the angle theta. I'll write it down over here. Let's say this will be theta. This is the angle theta, APB. And the angle ACB, let's say this will be the traditional gamma, angle ACB. The angle ACB, the interior angle, the magnitude of the interior angle at the vertex C, this guy will be gamma. I'll write it down over here. This will be gamma. Now, with respect to the triangle PCB, what role does the angle theta play? With respect to the triangle PCB, the angle theta plays the role of the exterior angle. And what does Euclid have to say about such angles? Well, let me write it down where, let's say over here, in his Elements, Book 1, Proposition 16, you can look it up, this proposition online free of charge, thanks to the monumental effort that was done by Dr. David Joyce. In this proposition, Euclid shows that the magnitude of the angle theta is strictly larger than the magnitude of the opposite and interior angles for the parent triangle. In other words, the magnitude of the angle theta is strictly larger than the magnitude of the interior angle at C and this little angle CBP at angle B. We do not care about this guy, we care about this guy. So now let's write it down. From this, we know that the magnitude of the angle theta is strictly larger than the magnitude of the angle gamma. That much we deduced. And what would your next step be over here? Well, again, put this video on pause, think about it, then come back and compare your ideas to ours. My idea here is the following. Let's concentrate on these two triangles over here, AMO and BQO. AMO, BQO. What can we say? What's going on over here? Well, remember the point P belongs to the perpendicular bisector of the line segment AB. What does that mean? It means that the length of the line segment PA is the same as the length of the line segment PB. That much we know. What does that mean? That means that the triangle AP, as in Peter, B, as in boy, is isosceles. that much follows from, yes, this is, we're setting up a contradiction, but that much follows from the geometry, from the underlying geometry. And we're given that the triangle AOB is also what? Also isosceles, because the distance from the point O to the vertices A and B is one and the same. And by Euclid's Elements, Book 1, Proposition 5, we know that the magnitude of this angle is the same as the magnitude of this angle. These are the proverbial angles at the base. And what does that, and what else we have here? Well, these two angles over here, this and this two angles are also, sorry, these two angles right here. Yes, these guys from here. These two angles are of the same magnitude as well, because the triangle APB is isosceles. And what does that mean? It means that the difference between the magnitudes of these angles is one and the same on both sides. So this angle right here and this angle right here is actually what? One and the same. The angles at the vertex O are what? They are vertical. And also in one of his propositions in the first book, Euclid shows that these angles are the same by magnitude. And what does that mean? That means that by angle, side, angle, the triangles AMO and BQO are what? They are congruent. And if these triangles are congruent, that means what? That means that the length of this line segment is the same as the length of this line segment. And more importantly, it means for us, the show of equal distances, that the length of the line segment QB is equal to the length of the line segment MA, because these triangles are congruent, and against the angles of equal magnitude there lie sides of equal length. But the triangle APB is what? Isosceles. That means that if we subtract one and the same magnitude, QB, from the length of the side PB and MA from the length of the side PA, we will have what? We will have exactly the same distances as well. In other words, we just proved that this distance right here, PQ, and this distance right here, PM, is what? Is one and the same. And that means that if we connect the points M and Q like so, we will have a triangle MPQ will be what? Again, that triangle will be isosceles. And we know that in every isosceles triangle, let me grab the chalk over here, this angle over here, let's designate this angle as delta. Let's write it down. The magnitude of the angle QMP, angle QMP will be delta. And what does that mean? What can we say? How can we tie together the magnitude of the angle delta and the angle theta? Well, the magnitudes of the interior angles in any Euclidean triangle sum to what? Sum to pi. That means that, let's write it down here, 2 delta plus theta is equal to pi. Would you agree? 2 delta plus theta equals to pi. This is from the triangle MPQ, which is isosceles. And that means what? That the angle delta by magnitude is equal to what? Pi over 2 minus theta over 2. That much we deduced and proved. Now think about what your next move be. Put this video on pause, walk away, think about it, and when you come back, compare your idea to ours. Well, here is my idea. I suggest that now we connect the lines, the points M and N, and look at the triangle MCN. What can we say about this triangle? Well, with our current drawing, this looks absolutely goofy and incorrect, and this is precisely the case. It looks goofy and incorrect because what we have here is a mathematical abracadabra, but this is the essence of generating a contradiction. We take the given assumption at its face value, we assume that it is true, and we plow right ahead. And this is what plowing right ahead means. We're told, remember, where is this condition? Here. The length of the line segment CM is the same as the length of the line segment CN. The distance from C to M is the same as the distance from C to N. That means that if we connect the points M and N, we'll obtain a triangle MCN, which will be what again? Isosceles, a show of equal distances. And this triangle is isosceles on the sides CM, CN. Again, going back to more than 2,000 years ago, Euclid, Elements, Book 1, Proposition 5, the magnitude of the interior angles at the base must be the same. So now we carefully mark it. The magnitude of the angle CMN, CMN or NMC, we designated with epsilon. And that means that the magnitude of the interior angle of this triangle at the vertex N is exactly the same. CNM or MNC is also epsilon. And on my diagram over here, because I did everything by hand and by eye, this looks a little silly, but you should be able to see that the magnitude of the angle delta, remember the delta over here designates the angle, where is it? QMP over here, QMP delta is larger actually than the angle epsilon, which is the angle NMC. And in order to let you guys see how this diagram might look like if it's done professionally with, for example, this free software that I use, GeoGebra, I will put this diagram on your screen for about 7 seconds so you can pause it and study it a little bit more carefully. Wonderful. Now that we understand what is going on with this setup, now let us proceed, and we're actually almost done. Can you see that we're almost done? Yes, you should be able to see that we're almost done. We know that the magnitude of the angle epsilon, from the isosceles triangle MCN can be expressed which way? The magnitudes of the angles epsilon, and gamma sum to pi. 2 epsilon plus gamma equals to pi, which means that the magnitude of the angle epsilon is what? Epsilon will be pi over 2 minus gamma over 2. That much we understand. But we also have proven that the magnitude of the angle theta is strictly larger than the magnitude of the angle gamma. Remember? Exterior angle, Euclid, Elements, Book 1, Proposition 16. So now we execute the following maneuver. I'll write it down here. Okay, theta is less than, the magnitude of the angle theta is strictly larger than the angle gamma. And this we take the numbers theta and gamma we take to be strictly positive real numbers. Now we multiply this inequality through by -1. That means what? We put the minus sign here, and we flip the sign, the relation between these two resultant numbers to the opposite. It goes like this. So minus theta is less than minus gamma. Would you agree? Yes. Now we take this inequality and divide it through by one and the same non-zero real number, 2. So we divide by 2, the inequality stays, nothing changes. And now we take that inequality and we add one and the same strictly positive real number to both sides of this, pi over 2 plus, and then pi over 2 plus. So here looks pi over 2 minus gamma over 2, pi over 2 minus theta over 2. What do we see here? Well, we'll see that this magnitude over here is actually delta, right? This is delta. And what is this? Pi over 2 minus gamma over 2. This is epsilon. This is the magnitude of the angle epsilon. And what is the relationship? What is the relation between them? We came to the situation where delta is less than epsilon, But this is absurd. This is exactly the contradiction. Why is that? Well, normally the point Q that lives in the ambient plane has how many degrees of freedom? 2, because it can travel into 2 independent directions. But due to the way in which the point Q was constructed, it has only 1 degree of freedom. Why is that? The point Q has only 1 degree of freedom because due to the way it was constructed, it can travel only along this straight line AN, this guy right here, only along this straight line and nowhere else. It cannot veer off. Only one straight line, 1 degree of freedom. And remember all our pedantic and perhaps painful insistence of being very accurate with our assumptions. Oh, I erased it. P is strictly between A and C. BP is strictly inside the parent triangle. AN is strictly inside the parent triangle. The intersection point Q is strictly inside the parent triangle, and so on. Well, this is precisely the contradiction. The only way this relation can hold that the magnitude of the angle delta is strictly less than the magnitude of the angle epsilon is when the point Q goes outside over here. Let me use, for example, this red. Like if the point Q is the imposter that goes over here, Q over here, then we connect the points M and Q this way, and then yes, the magnitude of the angle delta, this magnitude right here, let me show it this way. See, this way here, this way, will be what? Will be strictly less than the magnitude of the angle. This guy goes here, epsilon. Yes, then, but this is not the case. The point Q, remember, is located where? Strictly inside the triangle ABC. And because we did not make any mistakes in the entire chain of P then Q implications, our assumption that A is greater than B, or our assumption that the length of the side CA in the parent triangle ABC is strictly greater than the length of the side CB of the parent triangle was false, because precisely we arrive at this contradiction. And now that we strike out this, we eliminate this possibility. What is the next possibility? The next elimination round will be based on the assumption that the length of the side CA of the parent triangle ABC is strictly smaller than the length of the side CB of the parent triangle ABC. Before we jump to the next contradiction that is based on the assumption that A is less than B, here is what a contradiction based on the assumption that A is greater than B, carried out more professionally, for example, with a free software called GeoGebra, looks like. I'll put this diagram on your screen for about 7 seconds, so you have plenty of time to put this video on pause and study it in more detail. Wonderful. Now we assume that the length of the side CB of the parent triangle ABC is strictly larger than the length of the side CA of the parent triangle ABC, which is captured with this case that follows from the trichotomy law for real numbers. I will not be going into all the gory details like I did in the first case. I will just highlight or give you guys a guide following which you will generate exactly the same contradiction. In this case, we grab the point C and move it off the perpendicular bisector lowercase p of the line segment AB, not closer to the point B as we did in the previous case, but closer to the point A of the parent triangle ABC. In this case, what does it mean? It means that the perpendicular bisector lowercase p will intersect not the side AC, but will necessarily intersect the side BC. At the point P, it will be strictly between points C and B, which means that the line segment AP will fall strictly inside the parent triangle ABC. And this time, instead of connecting the point B with the point P, which we do not really gain any tactical advantage from doing that, we'll connect the vertex A with the point P. But in this case, the line segment AP will be what? In this case, the line segment AP will be strictly inside the parent triangle ABC. And when we intersect this line segment AP with the line segment BM, which is also strictly inside the parent triangle ABC, will obtain the point Q, just like in the previous case. And the point Q, now we know it's very important. It sits strictly inside the triangle, parent triangle ABC. And from that, we unwind the proof and arrive at the contradiction in exactly the same way. We prove that the cross-hatched triangles over here, AQO and BNO, are what? They're congruent based on which criterion? Angle, side, angle, the vertical angles over here. That means that the length of the sides that lie against opposite angles in these triangles are the same. It means that the distance BN is the same as the distance, where is it, AQ. It means that the distance PQ is the same as the distance QP. The triangle QPN is isosceles. We mark the angle delta for that triangle. We know that is expressed as a function of the angle theta, which way? Pi over 2 minus theta over 2. And now what do? Now again, we construct the triangle NMC by the problem statement. That triangle is isosceles. We introduce the angle epsilon. Here the angle epsilon is shown over here. We know the magnitude of this angle as a function of gamma is the same thing. Pi over 2 minus gamma over 2. Magnitudes of the angles at the base of the every isosceles triangle is the same. So from the assumption that theta is greater than gamma, here theta is what? The angle APB. This angle is exterior with respect to the triangle ACP. By Euclid's Elements, Book 1, Proposition 16, the magnitude of this angle is strictly greater than the magnitude of the interior and opposite angle, this one and this one. From this assumption, we already know how to proceed. Multiply by -1, flip the sign, divide by 2, add pi over 2, and arrive at the contradiction that the magnitude of the angle delta is strictly less than the magnitude of the angle epsilon. And this is possible only when? This is possible only when the point Q travels along the straight line BM over here, jumps some over here, goes like this. But this is impossible. We already proved that the point Q is strictly inside the triangle ABC. Contradiction, it means that we eliminate this case over here, and now we have only one case left in our elimination rounds, and we have to just analyze, is it even possible to have a Euclidean triangle under the conditions specified? Very good. In the previous segment, based on the assumption that A is strictly less than B, we arrived at a contradiction, which, rendered more professionally with the free software called GeoGebra, may look as follows. And now we recall that the trichotomy law for real numbers covers 3 cases, out of which we have eliminated 2. We eliminated the case that A is strictly larger than B, and we eliminated the case that A is strictly less than B. It seems that we're basically done, but unfortunately we're not done yet, because remember that the eliminate and conquer problem solving approach has a fundamental flaw. When it comes to a guarantee or doling out a guarantee about the prediction that all the suspects have been lassoed in, the eliminate and conquer problem solving approach cannot really give such a guarantee. So even though many students will be in a rush to do their PhD in mathematics or win their Nobel Prize in theoretical physics, which is always a noble pursuit, they will claim that they're done. But in reality, we still have to analyze the case when A is equal to B. In other words, we have to show that, pedantically, we have to show that under the conditions specified, it is possible to construct a Euclidean triangle really, and that triangle exists. And the way we can show it is as follows. For example, let's say we are given an isosceles triangle ABC, which is isosceles on the sides CA and CB, meaning that the length of the side CA is the same as the length of the side CB. And let us say that we picked a point on the perpendicular bisector or on the height of the triangle that emanates from the vertex C. That point O, we know that it is equidistant from the points A and B, from the vertices A and B, and then we extended these line segments BO and AO into the points M and N. Can we show that the points M and N are equidistant from the point C? Well, that much we should be able to show, to prove. We already pretty much went through this exercise. In this case, these triangles, the triangle AOM, this triangle, and this triangle BON, we can prove that these triangles are what? That these triangles are congruent by what? By angle, side, angle. And that means that if these triangles are the same, that means that the lengths of the sides AM and BN are one and the same. And precisely because our parent triangle is isosceles, this automatically means that the distances CM and CN are the same. And conversely, you guys can think on your own, maybe you come up with a better idea, but let's say we're given an isosceles triangle, which is isosceles on the sides CA and CB, and we're given 2 points M and N, which are equidistant from the point C. We connect M with B, we connect N with A. We want to show that the point O, thus produced, will be equidistant from the vertices A and B. What can we do in this case? In this case, we can probably argue that, for example, let's see, we know that CM is equal to CN by length. The side CO here will be what? Will be shared. So that means that by side angle side, these angles will be the same. These triangles CMO and CNO, these triangles will be what? They will be congruent. That means that the lengths of this side and this side will be the same. And then from this point, what can we show? If the lengths are the same, then we can probably show that the triangles, bigger triangles B, M, C, and A and C are congruent. That means that the length A, N, and B, N must be the same. And since these guys have the same length, these line segments must have the same length. So the point O will be equidistant from the vertices A and C, and by that virtue, it will be on the perpendicular bisector of the line segment AB. And now we are done by eliminating 2 cases and showing that the last remaining case does really produce a legal and valid Euclidean triangle ABC. We are pretty much done. And in order to confirm our ideas, our thinking, I put together a short animation using GeoGebra, and it will show that, for example, if we fix our isosceles triangle ABC as shown over here and come up with this construction and make at least one point run, let's say point M run along the side CA, or point N alongside CB, or point O along the height over here, the perpendicular bisector, then the remaining guys will be changing their position in unison, and it will be a completely legal and valid Euclidean triangle. And at this point, we are really done. All we have to do now is just write down the answer for the question that was posed in this problem. What is the magnitude of the remaining two interior angles of this triangle? And here the answer is not unique, because we proved that the parent triangle ABC must be isosceles, and if the value or the magnitude of one interior angle of this triangle is given without the specifics of which one, we generate actually two answers. What is the first answer? Well, let us assume that the magnitude of the interior angle of our triangle is this one at the vertex. So this magnitude right here, I'll write it down here, is alpha 0. What does that mean? Well, that means that the magnitudes of the remaining angles, will be what? The angles at the base. And for the magnitude of the angles of the base, let's say these angles are x, 2x plus alpha 0 is pi. So each x is what? Pi over 2 minus alpha over 2. So here we will write down the first answer will be alpha 0, and then pi over 2 minus alpha 0 over 2, and another angle pi over 2 minus alpha 0 over 2. This is our first answer, the set of three real numbers. Again, alpha 0 is the first angle, the magnitude of the first angle. Pi over 2 minus alpha 0 over 2 is the second, and pi over 2 minus alpha 0 over 2 is the magnitude of the third angle. Conversely, what if in this case we're given the magnitude of the angle at the base? Here, this guy is alpha 0. Then what does that mean? Well, that means that, again, we will have in this case, this will also be alpha 0. And what does that imply? It implies that 2 times alpha 0 plus the angle x will be pi. And that means what the answer for the second answer for this problem is exactly this. Alpha 0 is the magnitude of the first angle. Alpha 0 is the magnitude of the second angle. And what is the magnitude of the third angle? It will be pi minus 2 alpha 0. These are two, in general, distinct sets to answers. The answer is not unique. Of course, we see that, what do you guys think is the equilateral triangle, or the triangle whose interior angles are all 60 degrees, let's say over here, or pi over 3, is this triangle isosceles or not? Well, by strict definition, yes, we have to treat this triangle as also an isosceles triangle, and in this case our answers, two sets, will collapse into one. This situation, this problem will still work. But the theory of groups have something interesting to say further about this. The group of rigid symmetries of an equilateral triangle is what? Is D3. And it has, D3 has 6 elements in it. 6 congruence motions bring this triangle, this object into coincidence with itself. And the isosceles triangle that is not equilateral, has how many congruence motions? Only 2. The identity and the reflection of this isosceles, not equilateral triangle, about its vertical axis of symmetry, shown over here, P. This is it for the mathematical problem S2M38, and we will move to a new challenge next. As I mentioned earlier, this was the last episode in which we studied the eliminate and conquer problem solving approach in a dedicated manner. And starting with the next episode, we'll begin the study of the divide and conquer problem solving approach in a dedicated manner. That problem solving approach is also very popular, very powerful, and we suggest that you try your hand in applying, if you think you know how the divide and conquer problem solving approach works to the process of the generation of the solution of the next challenge. Our next challenge will be the mathematical problem S2M39. And in that problem, we're given a piece of wood that is 8 by 3 units in size, and we're asked to cut that piece of wood into 2 pieces of wood that can perfectly fit inside the 12 by 2 hole, and the original piece is 8 by 3 units. Which units, it doesn't really matter. But this is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will present my solution of the mathematical problem S2M39.